every 2 seconds, someone, somewhere in the world, will suffer from a stroke. Stroke is the second leading cause of death and the first leading cause of preventable disability in the world. So what happens during a stroke is that our brain cells are deprived of oxygen. And the part of our brain, the motor cortex, which is responsible for motor commands, becomes damaged. And that really degrades our motor function. So today, the most popular solution is therapeutic rehab exercise. So by completing a lot of repetitions of the same exercise, you can essentially rewire your brain and create new neural connections. But the problem with this is that this technique isn't very effective. And sometimes it can take even longer than 6 months for patients to recover. And only 10% of people who use this technique will recover fully. The other 90% will still face minor and severe impairments, which can greatly affect their quality of life. And I think it's just crazy that such a large issue is being, the technique that's used to solve such a large issue is so inefficient. And so this is where brain-computer interfaces come in. For my Replicate project, I made a game of Flappy Bird. And so basically our brains are made of billions and billions of neurons, and these let us react to the environment around us. And so these neurons act as like communication to and from the brain. So whenever there's a message that your brain needs to send anywhere to the body, it uses these neurons. And so it's like a chain reaction. Think of it like a game of baton pass. So the first neuron gets a message, and then using electrical and chemical signals, it passes the message on to the next, and then on to the next, and so on and so forth. So let's say you burned your hand. So let's say your finger touched a flame. The skin cells around your finger will let your neurons know what's happening. And then these neurons, like I said before, like a chain reaction, will transfer the message to the next neuron and to the next, and so on and so forth, until it reaches the brain. And then when it reaches the brain will process this information and then send some information back the same way. And you'll instantly flick your finger back to make sure you don't get burned. So when one neuron is activated, there isn't much of a measurable impact, but when large patches of neurons fire, we can measure that because the brain emits electromagnetic waves. So there's a few ways to acquire these waves. The two main techniques are invasive and non-invasive techniques. So with non-invasive techniques like EEG, you just place a few electrodes on your head, and then these electrodes measure the brainwave frequencies and then send them to a computer. So this is really good because EEG is cheap and it doesn't require surgery, so it's very safe for people to use. Now the alternative is invasive techniques like ECOG. And so with ECOG, you have to do surgery, and you have to drill a physical hole into your scalp and then place electrodes on the scalp of your brain. So this is great because there's less noise or interference from other signals, but it's very dangerous because surgery is required. So for my project, I use the Muse Headband, which is basically just an EEG device that you place on your forehead. And so this is some of the data that I recorded. So as you can see, there's a very clear spike up, spike down, and then it stabilizes back to regular level. And so what this spike is, it's a blink. So whenever I blink, there's a spike in the brainwave frequencies. And so this is called noise or artifacts. And these are usually avoided because that's not what you want to be picking up on. You want to be picking up on actual EEG data. But I actually use this to my advantage. So for my Flappy Bird game, whenever I blink, my computer program detects that spike of activity, and then it makes the bird move up. So if I blink multiple times, my bird will also move up multiple times. So Flappy Bird is really fun and all, but there's actually some serious application to this, especially in the medical industry. So let's take the example of stroke again. So what researchers do is they use EEG headbands like the Muse, and then they record your brainwave activity. And then using AI and other algorithms, they can find out whenever you're thinking about moving a certain body part. So for example, if I'm trying to move my leg, if I'm thinking of moving my leg and I can't actually use it, then there will be a very noticeable pattern a brainwave pattern. And this isn't easy to see like with the blink, so that's why you need artificial intelligence most of the time, and you need hundreds and hundreds of trials. And after you've detected this pattern, what researchers do is they take an actual robotic leg, and then when that movement is detected, they'll move the robotic leg in real life, so it acts like a functional replacement. And so researchers took this one step further. So there was a monkey who was paralyzed, and it couldn't control its right leg because of a lesion in its spine. So neurons were physically blocked from accessing that part, and so that's why the monkey couldn't move its right leg. So what neurons did is they used an invasive BCI, and they put it in the monkey's head, and then they put a wireless chip that bypassed the lesion. And once again, using AI, they found out a certain brainwave pattern that was associated with thinking about moving the right leg. And then when the monkey thought about it, they used the wireless chip to electrically stimulate the right leg, and it was like a functional replacement. I think this is crazy because we're literally solving paralysis using brain-computer interfaces. So people with disabilities are already using this technology, and I'm excited to see where else it can take us. Thank you.